So chi-square, this is on the back of your lab packet, people at home. Chi-square is a really important statistical analysis that you need to know. I asked y'all to fill out the first part of that chart. If you're at home and you have not done so, pause it and fill out that, the O minus E squared over E. And then the next thing you're asked to do, so chi-square, out beside all this, write null hypothesis. So null hypothesis, the simple version of this, y'all can look up the more complicated one, is the data that you, basically the null hypothesis says the data that you observe is statistically close to the data you expected to get. So if you flip a penny 100 times, you would expect to get how many heads and tails? 50-50. But if you got like 47 and 53, then that should still be statistically close to what you expected. So it's a statistical test to see if the data that you got, that you observed, is close to what you expected to get. Okay? So it's a way of checking that. And so in this case, you guys had M&Ms, and they had 4 different types, and they expected to get an even amount, and they got pretty close to it on all of them. And you had to calculate these O minus E squared over E problems. All right, so next thing I want you to do is go ahead and add up your, so chi-square is this formula. The squiggly E up here, which looks backward on the camera, this is an E. So it's Greek letter E, sigma. And so what does that mean? Math people, you mind? It means summation. When you see that, you sum or add everything up. So you're going to add up all those 4 different things. You're going to add up all the O minus E squared over E's. Go. Add them up. From your chart. Did you add them up? Nathan's looking at me like I'm crazy.
Wait, we add up all the ones in the last column?
Yeah, so you're adding up all the O minus E squared over E's in the last column.
Is it supposed to be like a decimal form or a fraction form?
No, it needs to be in decimal.
Just put it in that blank right there.
Put it in the blank. Chi-square, the 3 points. This is just going to be practice for us. I've got another one that's modified a little bit we'll do for a quiz. All right, so what is your chi-square value, Ashlyn? 1.04. Good. So when you add all those up, you should get 1.04. The next thing you got to do is figure out your degrees of freedom. So degrees of freedom are basically, the simple version of this is it's one less than the number of different things you looked at or calculated. So how many different things do we calculate? So what would our degrees of freedom be? 3. Good. So it's always one less than the number of different things you calculated the O minus E squared over E for. All right, so when you're looking at these probability charts, for our purposes, you're always going to use 0.05 probability, which means that the data is within like a 95% confidence range, okay? And so always use the 0.05 unless they say otherwise. Yes?
You're talking about the dependent variables for like the 4 things we calculated? Those are 4 things?
It's not dependent variable. It's just the different things you calculate.
Like the groups? Like
Sure, yeah.
Okay.
All right, so if you have, so based on your degrees of freedom and knowing that you have to use the 0.05 probability value, what is your critical value from the chart? 7.82, good. All right, so you're almost always going to use, unless it says otherwise, the 0.05 probability value, and then if you know the degrees of freedom, you should be able to figure out your critical value from the chart. Now, judging what you got on your chi-square value, do you think, in order for your data to be close to what you expected it to be, do you think your chi-square value needs to be below or above the critical value in order for you to say your data is statistically close to what you expected?
Above.
You think the chi-square value should be above the critical value? The chi-square value, the lower the number, what does that tell you about the observed and the expected? What did you notice?
Smaller change.
There was less change. It was closer to the expected, right? So the smaller the chi-square value, the closer it is to what you expected. So what you're going to look at is the chi-square value less than the critical value. If it's less than the critical value, then you're going to accept your null hypothesis, which basically means the data that you observed is statistically close to what you expected to get. Okay? You're going to have to do this multiple times. You almost always have to do it on the AP exam. It's just a statistical way of checking your data to see if it's close to what you expected to get. Okay? Any questions on that? Now, yeah.
How would we be able to find the critical value of something?
You're going to use this chart. You'll be given the chart.
Okay.
And on AP Bio, you're given all of the stuff you need mathematically. You'll be given the formula, and you'll be given the chart. You just have to know how to apply the data. Yeah.
So what is,
And you go ahead, Paul.
what are the 3 rows?
Yeah, I was about to say.
What 3 rows?
Like, there's 3 probabilities.
Well, that's what if you want to be within like 99% confidence or within like 99.9% confidence in your data. So it's just a different confidence level that you have in the data that you've collected. For most of our purposes, though, we'll be 0.05.
What did you say the degree of freedom was?
It's always one less than the number of different things you're looking at. So we looked at 4 different colors, so our degrees of freedom would be 3. If we calculated it for like flipping pennies on heads and tails, then our degrees of freedom would just be 1. Okay? So it's always 1 less than the number of different things you're looking at. All right. If you take statistics next year, maybe Kenny can explain that better, but that should give you what you need. Now, if you'll flip over, you're going to calculate this on the number of different cell types that we look at. Okay? So, you can see I've got all the different cells in different phases listed here. You're going to count how many are in each phase, and you're going to calculate an observed and expected value. And we're going to use our class data as the expected value, so we're going to average all that together. And then your group's data is going to be your observed. And basically you're seeing is your observed value close to what the class is getting. Is it not? If it's not, why is it not? Okay?